Hello and welcome back to the AI/ML track at PyData Global. Thanks for coming along. Up next, we have Python, BigQuery, and DataFrames, hands-on with scalable serverless analysis, ML, and AI with Tim Swena, Alyssa Williams, and Hsia. Without further ado, I will hand over to Tim.
Hey folks, yeah, I'm Tim Swena, and today we'll be doing some hands-on work with BigQuery DataFrames. Yeah, and my teammates Alicia and Wei will be there in chat to be able to help with any questions or problems that come up. But before we jump into the hands-on stuff, let's get a bit of intro. I'm not sure how many of you have worked with BigQuery before. I imagine many of you have worked with DataFrames before, but we have quite a different flavor that we're working with today. So just some quick background for folks that haven't used BigQuery. BigQuery is Google Cloud's flagship analytics product. So it's primarily a SQL engine. That provides big data, but it scales to small data to analysis in a serverless way, so you don't have to manage clusters or worry about any of that stuff. And it's powered by Google's very large infrastructure. There's both a storage tier and a compute component of this. So BigQuery can help you manage your storage in our native format, which if you've worked with Parquet, very similar in terms of, I think Parquet was inspired in part by the original Dremel paper. And you can store your data in Google Cloud Storage if you prefer to work with manage your own files. But if you don't, you can just have a logical table and let Google worry about storing those, replicating those, creating snapshots. And then on the compute side, it can scale up and down really at the drop of a hat. So if you're not running any queries and you're on the on-demand billing, you don't pay for anything. So it's only when you run that query, you pay for that query. If you want, kind of more dedicated resources and your company is using BigQuery a lot, you can save some costs and have some more reliable performance if you do buy compute separately. And then on the Python side, this is the one that I'm sure you all are very familiar with, pandas being kind of your community standard data frame for the last decade or so. We do have connectors to BigQuery that have been part of pandas, or now more in the pandas ecosystem. We have a package called pandas GBQ that my team also helps maintain. And the classic way of interacting between, BigQuery, this cloud world, and pandas is you write some SQL, you run that query, and you get back, a good chunk of data, load that on your notebook or, wherever you're running pandas, and then do some additional processing locally. And that's all well and good, but you have to write SQL. And your laptop might only have so much memory. If your data is already in the cloud and you want to get it to your laptop, that might be a lot of bandwidth, a lot of egress to worry about. And your company might restrict egress. So your company might want, hey, this data is in the cloud, I want it to stay in the cloud. And so BigQuery DataFrames is here to help with those problems. So the pitch for BigQuery DataFrames is that SQL part to get from your pandas code to BigQuery. For a lot of workloads, you don't have to write SQL anymore. You can use a very familiar API on the analytics side, it looks a lot like pandas. We try to be almost drop-in compatible where we can. Uh, and then there's another side of BigQuery, which is previewed here, which is BigQuery actually provides some ML functionality. And for that, we are very much inspired by scikit-learn. Um, but yeah, the gist is you write this, in this case, pandas-like code. We import bigframes.pandas. Read GBQ. That's actually, drop-in compatible with pandas GBQ, but instead of downloading this whole table to your laptop or wherever you're running pandas, this is just a pointer to that table, and that data stays there and doesn't have to move. And yeah, uh, many other APIs that we'll see hands-on today. And then on the ML side, we'll play with this a bit today as well. Um, Again, it looks a lot like scikit-learn, but it's powered by BigQuery ML, BigQuery machine learning. So you create your model, you point it at a data frame. Generally, this would be a BigFrames or BigQuery DataFrames object. Once you have that model, you can score, predict, and then serialize it. So rather than pickle files, you'll be serializing these models to the native BigQuery format. And we integrate with the rest of cloud as well as partners and open source. Um, One of the ways we do that, the Big Frames team has worked very closely with another team on BigQuery, which is the remote functions team. And so we provide an easy way to take advantage of the rest of Google Cloud so that you can run custom code and connect that to both SQL and Python through Big Frames. Um, and then we won't use it too much today, but we do also work very closely with our teammates in Vertex, um, the ones who make cloud connections to Gemini and all the advanced AI stuff that Google's known for. You can do that through Big Frames via BigQuery ML and Vertex connections. Um, so with that, I think that's probably enough intro. Let's jump into some hands-on stuff unless there's any questions. Not seeing any in the chat. So first thing first, for the folks that are attending the virtual conference, we have a coupon code for you. So this link should also be present in the resources tab. Um, I do recommend you copy this link and open it in an incognito window. The reason for that is if you're logged in as a Google account, um, it's going to create a coupon associated with that Google account right away. But if you're in an incognito window, it gives you a chance to log in and select which Google account you want associated with this coupon. I highly recommend using a gmail.com account. Um, it might be possible to use a corporate account, but very often, and has been the case when I've tried this out myself, your company will either block Google Cloud, um, or maybe it doesn't block Google Cloud, but it'll block you from creating a billing account, which is what this coupon code does. Um, the reason I recommend this is there is a free trial for Google Cloud, but that requires a credit card to sign up. But with this coupon, um, you won't need a credit card. You just use this link and go. Um, so just a quick thing. So once you log in, um, it's going to take you to something to create a billing account using that coupon code. You'll create that, and then it might ask you to create a GCP project. If it doesn't, if you click the little Google Cloud, it'll take you to a welcome page like this. And then if you look up here on the top left, that has what's called a project ID. You might not see one here. Um, But if you click that box, it should prompt you to create a new project. Um, and then from here, you're going to give it whatever name you want, and then you can associate it with that billing account for your coupon. I have a project that I'm going to be using for this demo. Um, but yeah, I'll give folks a chance to sign up for that. And while you do that, just a note for folks that might be watching a recording of this, or maybe the coupon code didn't work for you. Much of what we can do today, you can do in what's called the BigQuery sandbox. So BigQuery is one of a handful of products on Google Cloud where you can actually use a version of the free tier without a credit card. Um, there's a couple of features that we'll be using today that you won't be able to do. The big ones being BigQuery has Python notebooks built into it. For that, you can either use Colab or a local Jupyter notebook, as well as the ML features. You won't be able to do that with the sandbox mode, but you can skip those, and I'll point that out as we get to them. Um, and then, yeah, if you are using an environment that isn't the notebook that's built into BigQuery, there's something I didn't put in the code lab that we'll be going through. You'll have to set this option here so it knows which Google project to send requests to. Um, and yeah, so for folks, yeah, this is just I think I just showed you folks that how to click the new project button and select a project. And yeah, for the folks doing sandbox, this is what your collab window might look like. But hopefully that's enough time, or folks can catch up or ask questions in the chat if you're stuck. Um, Next up, this link should also be in the resources tab. If you go to this, it's going to go to our Code Labs website, where I've got our hands-on demo prepared for you all today. And it should look like a lot like this. So I've got all the steps we're doing on the side here. Um, there's a lot of words. I'm going to summarize them. I'm not going to read to you today. Um, but the gist is we're going to do some analytics together and a bit of machine learning using BigQuery DataFrames together. So the first thing, a lot of you should probably be on the Cloud Console already because of that coupon code. But if you're not, you can click this link here. It'll take you to console.cloud.google.com, page like this. And then we're actually going to want to go to BigQuery. So you could click this link too to get to BigQuery, or in future, you can click this search bar up here and type in the word BigQuery. And it's this first one, BigQuery Data Warehouse / Analytics. And that'll take you to BigQuery. And then, yeah, we're going to be using the Python notebooks today. So if you're on this home screen, there's a nice big button here to create a new Python notebook. You might not always see this home screen. So if you don't, you can click this arrow and create a new Python notebook that way. The first time you do this, it's going to ask you to enable some APIs. Since this is a project I've used before, I've already done that. But it'll show up on this side here. And then once you've enabled the APIs, then click this connect button, and that'll create a virtual machine associated with this notebook to run our Python kernel. And then as that goes, this step might be optional. I think the Colab or BigQuery notebooks have caught up to the latest version of BigFrames. but this will make sure you're using the very latest version, because that's what I tested the code lab with. So yeah, we see we've got our machine here. So it's got the RAM and disk. So that's how we know it's connected, and our installation worked. So that's kind of the setup. Um, and yeah, if anyone's stuck, please feel free to ask in the chat or the Q&A. My teammates are happy to help. Um, and yeah, so let's get started. So we've got our import here. You saw that in the slides. I'm also doing something a little different today. So I recommend setting these two settings just kind of as a best practice. I'm hoping to make these the default at some point in the future. Um, BigQuery DataFrames or BigFrames tries to mimic pandas as best we can. Um, and as part of that, a pandas data frame has, a well-defined ordering over all your rows. So you can ask for row 37, and pandas will give you row 37. We try to do that as best we can by default in BigQuery data frames, but as you can imagine, since there is no fast access to a particular row unless some specific requirements are set, like a primary key and clustering column. Um, so it's quite expensive to say, hey, I want a total ordering over all my rows. So if you want to turn off that feature, use this one. Um, and then this display repr mode. Um, Normally, if you're in a notebook and you try to visualize a data frame, it's going to go and run that query and show you a preview. That might be a bit overkill for what we're doing today. So if we set repr mode equals deferred, we won't be running queries unless we explicitly ask to download some data to the notebook. Um, so to get started here, I copied from and one thing you might notice I'm doing, or maybe missed, there's this copy code sample button. That's going to make it real quick, so you don't have to highlight and copy. You can just click that button, and it'll copy the code sample to the clipboard. I think just about everything is going to be copy paste. If you have to modify these, I will let you know. Um, so the first like real big frames code that we're running today is we're going to read from this table. So this is, as you can see, from our public data sets program. Um, and the government of Iowa actually publishes um, anytime a store purchases a retail outlet, be it a liquor store or restaurant, buys alcohol. Uh, Iowa records that in their database, um, and we have made that database available on BigQuery now. So we've got a pointer to that table. So we didn't download that whole database. It's actually pretty large. I think 7 million rows or something. But yeah, so we've created a pointer to that. If you want to learn more, I've got some links here. Um, yeah, and aside, Iowa, for a while, I think up until the 80s, Iowa actually was the only place you could buy liquor as a person was from state-run retail stores. And in the 80s, they kind of privatized it a little bit, but all those retail stores now still have to buy from Iowa. So Iowa's the state government is a middleman for all the alcohol sales. Um, Next thing I'll show you. So this is a rather large table. If I want to just take a look at this, um, normally in pandas you might use .head. .head has a very specific meaning though. Head in pandas means give me the first few rows. And since we're using this partial ordering mode, that first is not defined. There is no ordering that we've set on this data frame. So instead, we recommend using an API called Peak. And that says, hey, download an arbitrary selection of rows. So behind the scenes, this is generating a select star with a limit clause, um, which is going to be a lot faster than trying to order all your rows and then download the first. So every time you run peek, it might give you a different result, although because of the caching that BigQuery does, it tends to be about the same. So here we can see a selection of the different values uh, and quite a few columns on this table. We'll dive deeper into the columns soon. Um, so here, just like pandas, we have .d types. And we have a local copy of BigQuery calls it the schema. So we know what all the column names are and what all the types are. And then you'll notice these look awful pandasy. Um, so this BigFrames package does try to emulate pandas um, as best we can. Um, a lot of these we are using the arrow D type. We find that arrow maps much more closely to um, what a true database engine would do, especially with respect to nulls and um, for floating point treating nan as a separate value from null. So we try to emulate the arrow type wherever we can. BigQuery does have geometry, um, or I think BigQuery calls it geography, but we're emulating the GeoPandas geometry type here for those geography columns. And then, yeah, for int and float, you'll notice the capital I and the capital F. That means we're using the nullable version of those types. Um, we might change this to emulate arrow in future as well, just because that is closer to how BigQuery acts and closer to what we actually do. Um, And then, yeah, let's learn a little bit more about this data set. So we're going to do describe all. So this is actually, going to query the whole table, every column, and get some summary statistics. So it's not necessarily a cheap query to run, although this is a kind of medium-sized table. So we're working with 7.5 gigabytes here, so it's not too scary to do. But you could filter this down before you call describe if you want to just describe the last 30 days or something. But yeah, that ran relatively quickly. So let's just take a peek here at what we can learn from this describe. Um, and just a kind of motivation for what we're doing. Um, Kind of just doing some exploratory uh, analysis today, learning what we can about this table, and maybe discover some insights together. So the first thing we notice here is this invoice and item number, the count, which I think this counts non-null values, um, is equal to the number of unique values. So potentially we could use that column as, and how many rows are we working with today? We've got about 30 million, just over 30 million rows. So I underestimated when I said 7 million. Um, so we've got just over 30 million rows with unique values for each of them. So we could use this as an index. We don't actually need to use that for anything we're doing today, but that is something you could try out, is set this as the index column, and then more of those pandas features will become available to you. Because right now this data frame doesn't have an index associated with it because of that partial ordering mode. Um, and then we've got some more categorical columns here. So we've got our store number. So we can see um, there's about just over 3,000 different retail outlets where you can buy alcohol that's logged on this database. Um, Although there's a few more names than there are IDs, so I might be curious to find which stores have multiple names associated with them. Maybe we could discover some data quality issues or some other interesting things about the history. Um, then, yeah, some more. categorical type stuff. And then as we get far to the right here, we get into more of the numeric column. So these are, your min, your max, your mean, and some approximate percentiles. Um, so we can learn a lot about the distribution just with describe. So, and this is basically drop-in compatible with pandas. I think we have a slightly different name here. I think pandas calls this unique instead of n unique. Maybe we'll try to fix that in future in a 2.0 release or something. And then, yeah, so we took a broad stroke at the data with this describe. And then just looking at these D types, there's a few ways I might categorize what we're looking at here. So we've got our unique key, and then we've got date. So we could potentially do some time series stuff. BigQuery does have some relatively sophisticated time series features. We won't dive into those today. And then we've got our kind of geography type stuff, city, zip code, county, the actual stored location. And then we've got some information about the actual item and what that is. So we've got these more categorical style or just qualitative style information about what was sold, as well as quantitative and uh, how many bottles, how many liters, how many dollars was the sale. So for the start, I was curious about more the geographic distribution. So let's dive into that and explore that some. Um, so here, I'm going to group by zip code. So um, we're going to aggregate over zip code. And then I want to see how much alcohol is sold in each zip code. And I thought it was fun to think about things by volume. So, like, just sheer amount of liquid sold in each of these zip codes. And if I run this, um, so here I am explicitly asking to download some data. In this case, I'm explicitly asking to draw a histogram. So BigQuery DataFrames has a subset of the um, plotting functions built into pandas. Histogram being an important one for big frames because that's one in which there's an extra layer of aggregation that happens. So we are actually calculating all of these bins via SQL. So we're calculating, how big each of these bars are in, and then only sending, these 20 numbers back to the client. So it's quite efficient in regards to how much data um, we're sending back. And then just to kind of describe what's happening in this chart here, at the bottom, we have our bins. In this case, this is liters sold. And then here for frequency, that's actually how many zip codes um, are in that bin. So we can see most zip codes don't sell all that much in terms of volume, but we do have a handful here that sell quite a lot of liquid. So let's dive into that a little bit more. So here, this code sample. Let's see which zip codes are selling the most. So here I'm taking that aggregation we did here up here. So still our sum of volume over each zip code. And we're sorting it. So we can sort by the volume sold with ascending equals false, because that's the pandas way of saying, hey, sort in descending order. And then the big thing to note here is we do call head. So previously, with just the data frame, I can show you this. Since we're in this partial ordering mode, if I call head up here, this is actually going to crash and say, hey, operation head requires an ordering. And that's because this table doesn't have an ordering associated with it. So head is very ambiguous in terms of what it would mean. So um, just to be safe, we point you in the direction of using peak But here we have explicitly sorted our data frame. And so no head does have a meaning. So we're saying, hey, sort by this volume and descending order and give me the top 25 zip codes. Um, and then here I'm saying, okay, I've already pre-aggregated. I've already done my limit by 25. Let's just download all of that data to the notebook. So I'm any big frames object, be it a data frame, a series, an index, you can call .2pandas, and that will say, hey, go execute this expression, this query associated with that object, and give me back the results as a pandas data frame. And we try to encode the best practices in terms of how to get that data frame to you as quickly as you can. Um, and then here we're just doing the normal pandas bar chart. Um, and right away we can see, these zip codes that sell, almost 5 million liters over the course of this database. Um, but we also notice a few other things. So I noticed these zip codes here. We've got 50314, and then we've got 50314.0. So that's a big red flag to me that, hey, maybe there's some data quality concerns here, some cleanup that we need to do before we really dive into our zip code analysis too much, because we've got, these basically duplicate zip codes, but some way or someone, either in the collection of this or in the pipeline that made its way to BigQuery, I suspect it's there in the source data. Um, Someone had converted this to a floating point number, which, yeah, you really shouldn't treat zip codes as point data. They're actually stored as strings in BigQuery. Um, so let's do that cleanup and rerun this analysis. So here I'll show you a few things. So just like before, we're doing read table. I could have used the df object from before, but since I'm creating a new df, I figured I'd just start over. And then here I'm doing, and this is something you can do in pandas as well. So maybe you're learning some things. I personally prefer this method chaining style of um, of working with data frames. So I'm using dot assign, and then I'm saying, hey, this zip code column, replace it with, and then this lambda is just saying, hey, use the previous data frame. So this doesn't have a name yet. Um, and so we're going to say, hey, use this data frame that doesn't have a name, grab the zip code from it, and then we'll do our string methods. And specifically, we're going to replace those dot zeros with an empty string. Um, BigQuery DataFrames, we have implemented your normal pandas, hey, just mutate the df object. So I could have written this as, df equals my read gbq, and then df zip code equals, df zip code string replace. But I prefer the method chaining style, so that's what I did here. It's equivalent, but we support both ways. We've embraced the pandas. There is more than one way to do things. Um, and then I'm doing that same aggregation, that same bar chart. So if we see down below, it actually looks a lot smoother, a lot less bumpy. And since we combined those two 50314 columns, they've now jumped up here. So um, it's actually, yeah, more than 8 million. So it might be interesting to also do that histogram now that we've kind of smoothed the data out and cleaned it out. Um, but yeah, I just wanted to do that to really stress exploring your data in this way, like, having some curiosity and trying to, discover some things, just high level stats like this can very quickly surface these data quality problems. Um, and so, yeah, I very much recommend this interactive working with data And it's something you might not have done if you were just tasked with writing the SQL code for this. Um, so it definitely highlights the power of these, data frame APIs that, we've grown to love in this PyData ecosystem. Um, so the next thing I want to do, I want to dive further into this zip code stuff. So we see that, there's some zip codes that don't sell much alcohol at all, some zip codes that sell quite a lot. And I have a hypothesis. And that hypothesis is, well, maybe some zip codes have a lot more population than others. And so for that, we're going to actually use another public data set. Um, so the federal government, the Census Bureau, publishes not only the 10-year census data, but they also do these surveys throughout the years. Um, and those surveys are aggregated in all sorts of ways by state, by county, by zip code. And so here we're using this zip code tabulation area survey from 2020. And we're going to use that to kind of grab our population data. Just like before, this is not downloading the whole census data to our notebook. This is just a pointer. That data frame represents a pointer. And now we're going to actually uh, do some actually pandasy things. So if we look up here, this volume by zip, we did a group by. Um, and you may be familiar with the fact that whenever you do a group by in pandas, that sets the key of the group by to the index of your data frame. Sometimes that's really annoying, and you end up doing these reset indexes to get rid of those. In our case, that's really useful because this provides a natural join key because we know that zip code is unique, and it's exactly what we want to join by to get this census data. So we're going to join by this census GeoID column. Um, the Census Bureau uses the actual zip code number as the GeoID in the case of zip code tabulation areas. So um, we don't have to worry about transforming from one to another. I have some other demos where we do that transformation, but in this case, GeoID and zip code, basically the same thing, at least in these terms. Um, so the other thing you'll notice, those two commands ran really quick. That's because they're just creating a pointer. I didn't run any queries yet. Um, and so now I do want to run some queries. Um, so yeah, I'm going to create a scatter plot this time. So I just want to compare that volume sold that I already aggregated with the total population that was reported from this Census Bureau survey. And here we go. So on the bottom here, we've got each dot is a zip code. At the bottom, we've got our population, and on the left here, our y-axis, we've got the volume sold. So we can see my hypothesis seems to be pretty correct in that, the smaller population zip codes didn't sell as much volume of liquor, and our higher population zip codes did. But there is quite a bit of variance here. But let's fit a line to it and see how it goes. So now is the step where if you're using that BigQuery sandbox, um, this calculate correlation step won't be available to you. You do need a billing account in order to use the ML features of BigQuery. So you can skip these steps if you're following from home and using that free sandbox. But for folks with a coupon, you should be able to run this just fine. It's relatively cheap because we're working with pre-aggregated data here, so only a few rows to fit our line here. Yeah, just some uh, notes about this. So this, like I said, is modeled very much after scikit-learn. since linear regression is one of the models in scikit-learn, we even tried to, I didn't use any parameters here, but we tried to get the module name and any parameters for the module to match scikit-learn as best we can. There's a few extras in here that are BigQuery ML specific, so it's a bit of a mix. It's not quite a drop-in replacement in the way that the Pandas APIs are, but it should at least be familiar. So here we're taking our features. So the thing that we're going to use as kind of the feature to make the prediction is the population, and we're going to guess that the population will tell us how much liquor volume wise is going to be sold. So that model, linear regression, runs relatively quickly. Let's just see how well we did here. So we can do the score function. I didn't set aside an evaluation data set or any of those ML best practices. I'm just saying, okay, how well did we fit the training data? We have a train test split method, just like scikit-learn does. If you want to do things a little more rigorously. But here we can see we've got about a 0.6 correlation, which is not bad. It is correlated, but yeah, this is not the sole predictor. At least individual zip codes are not the sole predictor. And then I wanted to do something a little fun, so um, I'm going to take a local. So here I'm importing pandas. I'm importing NumPy. There's nothing special about these. These are your standard downloaded from PyPy pandas and NumPy packages. So I'm going to create a local series in this case, from 0 to 49,000, and I'm going to actually do something kind of interesting. This was suggested to us from a customer, actually. Um, so previously, a few months ago, you would have had to take this local series and say, hey, explicitly convert this into a big frames object for me. But a customer said, hey, it would be convenient if I could do these ML functions, these predict functions, these fit functions on local data. So we've encoded some best practices for how to get data from the local machine into BigQuery as quickly and as efficiently as we can. So when you call predict, we get that data into BigQuery and then point BigQuery ML at it. So we get ourselves some predictions. We'll do that same scatter plot that we did before, but now we'll also add a line plot using those local data, as well as I converted those predictions back into a pandas data frame, or I think series in this case, and downloaded those. So yeah, we've got ourselves a line chart here. So we've got our scatter plot as well as our best fit line. Um, so there's a vocab word that I learned for this. um, so if you look at this line, you can see it's a pretty good fit as uh, the population is small, but then things get wider and wider as the population grows. And that change in variance is called heteroscedasticity. Quite a mouthful of a word. But the gist is, yeah, the variance is growing as the population grows. So this is kind of I had a thought here that maybe um, the thing we should be measuring is just like the per capita consumption. Maybe that's actually pretty constant. So that's what I'm doing here. So we've got um, volume per pop. That was, just this regular bar chart we had before. I'm filtering out the zeros just so I'm not dividing by 0. I don't think it would break anything if I didn't do that, but um, I forget. um, and then yeah, I'm doing that method chaining again. I could have done uh, mutation here, but I'm saying okay. I want a new column, and I'll call that liters per pop. So this is the per capita consumption in liters over the course of this whole data frame. Um, and so to do that, I'm just dividing these two series from the same data frame. Um, and then we plot that. And we see a pretty straight line here with some kind of wacky outliers. Um, where there's barely anyone that lives in this county, but there's, a lot. Um, so I have a few hypotheses about that we'll get to. Um, but before we do that, I want to do my best fit line again. But since this is basically a constant, I don't need to use machine learning really for this. It's just a pure average. So for the folks at home, this step here, you can actually pick back up if you're using the sandbox and don't have a billing account. This is not using any machine learning anymore. Um, so you can follow along again. Um, so yeah, I wanted to calculate the average in two different ways. One is kind of that per capita that I was getting at. So in the whole state, um, how much liquor? So add up um, here. Add up all the liquor sold statewide. So this is just a repeat of what you've seen before, doing that cleanup. Um, Here I'm downloading well, I'm not downloading, it's staying in in BigQuery. Um, I am creating a pointer to this statewide aggregation. So Census Bureau survey aggregated statewide. Um, and then I'm setting the GeoID column here as the index so that I can just grab Iowa from there. So how much liquor was sold in the whole database, volume wise, and dividing by the population from that statewide survey. So I could have summed up the zip code survey, but since the Census Bureau publishes these statewide surveys, I decided to just grab that individual row, and we can do that in big frames. So this is a big frames data frame with an index column as this GeoID. So I say, hey, that total population column, give me the row with index 19. And 19, if you look it up, is the GeoID for the state of Iowa. So um, that gives us this average here, which is around 88 liters per person over the course of however many years this database spans. And then the other kind of average I wanted to do is um, what is the average per zip code? So what does, in each zip code, we've got an average, and we're calculating that uh, previously. Calculated that up here to make our bar chart. Let's just take the average of all of these points. And that gives us a slightly different number. So we've got around 67. So um, there's a lot more zip codes with maybe less people that drink less than maybe some of the higher population zip codes are bringing the statewide average up. Um, so we can plot those two lines. This looks just like before with the other line, but in this case, uh, I'm not doing anything really fancy here. I'm just, yeah, creating my scatter plot and then creating some local lines of those two averages. Um, Magenta and red are maybe not the best choice of colors. Um, so yeah, we could change this here to do green. Um, and might be able to see the two difference. So yeah, we could see the statewide average is a little bit higher than the per zip code average. Um, so lots of other questions we could investigate. Curiosity is a great thing in data analysis. So I would definitely be curious why these outliers are here. One hypothesis I have that I have not tested that I would leave as an exercise to you all in future is, maybe some of these zip codes are just like really a commercial area that's surrounded by a higher population area. So I wonder if those outliers would start to disappear if instead of aggregating by zip code, we aggregated by zip code and surrounding zip codes. Something to try out in future. But I'm going to transition a bit here and look at a different aspect of the data. So I mentioned before, we've got kind of that geographic side, and we really dived into that today. Um, the other side I want to look into is the types of liquor sold, because I'm really curious about that. So we're going to start over again here, get ourselves a pointer to our table. I'm not going to do the zip code cleanup in this case because I'm not looking at zip codes anymore. Um, but that's something to keep at the back of our mind of, yeah, maybe we need to adjust the pipelines here to to clean that up. But I want to look at that category name column. Um, so if you remember before, we had a bunch of you can do .d types to see all the different columns. I just want to look at category name specifically. So let's do that. So it was category name. Um, Most of the time I do the square brackets. It is nice to do, um, the dot notation too in pandas. We support both. So just wanted to highlight that. Yeah, so we've got 103 different categories of liquor in this database. Let's take a look at those. So let's do some aggregation. So group by category name. And then just like before, I'm attracted to this idea of volume of, just visualizing this amount of liquid, in this case per category instead of per zip code. And let's do the same trick as we did before. We're going to sort. There's only 100 things. So I guess I could have done dot head here. Downloading 100 values versus 25 values didn't make too much of a difference. So I do the head once it's a pandas data frame this time. Yeah, and this not fitting the best here. I'll try to collapse it a little bit. Maybe zoom out slightly again. So yeah, we can see as far as these categories go, American vodkas are the best seller in terms of volume anyway in Iowa. We've got Canadian whiskey, spiced rum, a different type of vodka, different type of whiskey, etc. Um, so that's interesting to see. Um, but honestly, I don't care too much about like specific types of vodka and specific types of whiskey and specific types of rum. I'd very much like to find out a little more, the drinking habits in terms of the broader categories. These are still pretty narrowly defined categories for my tastes. So we're gonna do some uh, interesting stuff here. So um, these category names have a bunch of words in them. We're going to split those words by space and then call explode. So this is, again, a very pandas compatible thing. You could do this on a series, a string series in pandas. We're doing this all in SQL because that's what gets compiled to. Um, and so let's look at like bar chart, just like we did before, but this time instead of by volume, it'll be word count. Um, well, I guess I did plot. Oh, I don't know what I'm plotting here actually. Um, but yeah, we've got words. So we've got whiskeys, American vodkas, um, and there's still a couple of problems here. I see vodkas and vodka. I probably want to group those together at some point. Um, and yeah, if we look at how many unique words there are, um, So this category parts, that's my split category name. If we look at how many unique words there are, there's 113 unique words. We started with 103 categories. So we didn't actually get any broader categories per se in this case. We still have a little over 100 different things. So let's work on that. And to work on that, one thing we could do, so I mentioned we've got vodkas and vodka here. There's a basic natural language processing technique called, oh, I just made a query. I'm going to create a separate notebook to do a little bit of kitchen magic. But there's a natural language processing technique called a stemmer. Um, and we're going to use the Python package NLTK to do that. It will be important later on to see what version of NLTK we have installed. So I'm just going to show that here with the import. And this stemmer is here. So this is one of the stemmers built into the natural language toolkit Python package. This is not in BigQuery at this point. We're just working on our local notebook, playing around with some analysis here. So we've got our stemmer. So if we take what we had before, my vodkas, and stem that, we get vodka. If we take vodka, we should also get vodka. So that'll take our plural and turn it into the same thing. Um, let's see on a more irregular sort of spelling. So we got whiskey with EY, that's the American spelling of whiskey. And then we got whiskeys. If we paste that in, our stemmer chopped off the suffix part and turned it into a singular, but no one spells whiskey this way, as far as I know. So we've got whiskey with an I and whiskey with an EY. So it's not quite as smart as I would like. NLTK actually has uh, a smarter version of this called a lematizer. So stemmer basically says, "Hey, we're just going to chop off the suffixes for you." Lematizer says, "Okay, we'll chop off the suffix, but we'll try to find actually the base word in a bit of a smarter way." Um, and I'll be using the WordNet lematizer, which I think is actually a neural net sort of thing that was pre-trained. So the first time we run this, we're going to download that WordNet data, um, and then run our lematizer. So now whiskeys ends up with whiskey with a Y, which for our friends in Europe is how you tend to spell whiskey. It still looks a little weird to me as a American, but yeah, we can lematize whiskey, and that also goes to whiskey. Unfortunately, this WordNet um, still didn't seem to know about the differences between American spellings, or considers these different words for some reason. So we've still got whiskey and whiskey. So I'm going to make one more tweak to this, and this is, very specific to the data set I have. I'm going to make a lematizer where I convert into the American spelling because, I'm biased that way. So I've just got a regular dictionary here, and I say if I see the European spelling, I'm going to convert it into the American spelling. And if we run that function, we should see the American spelling now when we run our whiskeys. All right, so that's all local. So we kind of have a way of getting combining some of these words that we want to combine to get our broader categories. Let's get this to a point where BigQuery can actually use this. So the first thing I'll do is I'm going to set a variable called project ID. And the value you should pick here, it might be the actual name. Um, oftentimes we try to get the name equal to the ID, but the ID needs to be globally unique, whereas the name can be whatever. So here you can see down here, I created a BigQuery sandbox project, but if I were using that, I would want to use this ID part and grab that. In this case, um, it is just the same as the name, but I'm going to grab that project ID that I'm using for this notebook, paste it in here, just so I can use that later on. Um, and just to kind of let you know what I'm doing here. So I'm trying to use remote functions. I've actually run this before, so the service account already exists. Um, but I'm trying to use what are called remote functions in BigQuery. Um, so that's where we can point BigQuery at a web server somewhere and use that to run custom code. So in this case, I'm getting ready to deploy to Cloud Functions. Um, and I'm creating a service account to associate it with that cloud function. And that's more for a safety thing. I want to create a service account here that has no permissions associated with it because this lematizer function that I'm going to publish that doesn't need any access to any of my other cloud resources. So this is kind of a best practice I'm showing is like try to minimize the permissions that your functions that you deploy have. So I'm creating this service account that has no permissions on my Google Cloud resources at all. Um, then I'm just going to create a data set to hold this function that I'm going to deploy. I'm calling it functions in that project. You can call it whatever you want, but functions seemed appropriate um, for what we're doing here. And then you'll need to enable some APIs. For sure, you'll need to enable the Cloud Functions API because that's where we're deploying. I believe you might also need to enable the IAM API. Um, I had to do that yesterday, but didn't quite make it into the code lab. So um, yeah, run this to enable the APIs. It ran pretty quick in my case because the APIs are already enabled. It might take a moment or two for you folks to get that Cloud Functions API enabled. And then I'm going to run this function here. Oh, and since I'm in a different notebook, I do need to import BigFrames again, but you all can do this in the same notebook, so you shouldn't have to do this step. Yeah, so basically this is exactly the same function we had before. It is kind of important that we have the type annotations here. That's so BigQuery knows, how to serialize and deserialize the requests and responses we get from this web function. But other than that, it's just our standard Python code. And then I've put this decorator on here. Um, so I'm saying what data set I want to deploy to, what the name of this function is. Um, and then since we are using that NLTK package, I want to make sure that that image I build that I deploy to this web server has that package available. And that's where getting the version number was kind of important is you don't have to specify a version number. It'll download from PyPI and install whatever. But since I did this local testing with this version, I want to make sure I deploy with that version. So I know that what I did locally is going to be the same as what made it to the cloud. And then these last two settings are, again, those best practices. So giving it a service account that has minimal permissions, just the permissions you need to run this function is going to be important. In this case, I didn't need any cloud permissions, so I've got a brand new service account. And then I don't need this to be accessible from the internet. So I'm setting internal only. That way, BigQuery can access this cloud function, but some random person on the internet can't access this cloud function. It's going to be internal to my cloud network. So I do recommend that as a best practice too, unless you have some specific like cross-project networking requirements. So that deployed a lot quicker than I expected it to when I ran this. It's probably the first time you run this, it's probably going to take you 2 minutes at a minimum. So I apologize for the folks that are um, following along. If you haven't run this code cell yet, please do, because it might take a while. Um, that cloud function deployment is the thing that takes the most amount of time because we're creating a new server and all the networking stuff associated with that. Um, Side note, cloud functions is again one of those kind of serverless. I'll throw in air quotes. It is a serverless in terms of the marketing term. Obviously there are machines that are running your code behind the scenes. Oh, I need to grab that project ID because I'm switching notebooks. Um, so it is running on real machines behind the scenes, but the important thing to know is if this function isn't being used, since we're using cloud functions, it's going to scale that down to 0 unless you configure it otherwise, to keep an instance up if you want. So that function is deployed already for me. So I'm going to point BigQuery at that. So I'm going to do this read GBQ function to say, hey, I want to use that function that I just deployed in that other notebook, and call it lematize. Technically, this is optional if you're using the same notebook, but because I gave it a name, and you probably don't want to deploy this every time you run the notebook. This is kind of the best practice I recommend for that too, is to call read function on a named function. And then here I've got, in this case, a BigFrames series. So I get that into the cloud, and then I run this function against it, and I get back, my lematizer. So I've got all these different flavors of spelling whiskey, and they all came back as the same lemma, which is exactly what we wanted. All right, so that's remote functions. Oh, and yeah, this deployment step probably won't work for folks on the BigQuery sandbox. Um, yeah, there's not too many ways you can deploy uh, code to Google Cloud without an actual billing account. I don't believe Cloud Functions is on that list. So unfortunately, you'll either need to sign up for a free trial with a credit card if you want to follow along for that step. But if you don't want to run the lematizer, you could find some alternatives where you're not using remote functions to do the same thing. Yeah, so we've got that. Let's get back to our analysis. So um, I have a goal in mind. So I have all these categories, 103 of them that we saw before. Um, what I'd like to do is take each of these categories and figure out, okay, what word am I going to use for that broader category? So, for example, this 100 proof vodka, I would love it if it maps to just the word vodka. And that way, all the other vodkas in here also map to vodka. Um, Same for tequila, everything else. Try to map to, that broader category. So just start with a chart here, just counting how many orders have we had. Um, so size is just number of rows. So how many orders have we had um, for that particular category? And then we're going to do our split again. So I'll run this. Um, a lot of warnings. There's a way to hide those warnings. I probably should have put those in the instructions, but um, these warnings should go away once we call this unordered mode GA, hopefully soon. Um, but yeah, what I'm doing here is just like before, I'm splitting by space. I'm lowercasing to standardize because that seemed to be what our lemmatizer liked. Um, and then I'm doing one trick before I call explode. Um, so I'm creating a new column called numWords. So I'm trying to count how many words were in that original category name. So here I'm taking that words column that I just created. So this is an array. Um, and if we emulate that with an arrow array, so this is an array. Um, it's kind of funny, like in pandas, the way you count how many elements are in an array or in a list is dot stir. Um, Yeah, I've actually contributed a bit to pandas with regards to the struct data type. Might want to do something like that for array in future, just so we can mimic that and reflect the actual type before. But we've made sure in big frames, if you have an array type or a string type, .ling will work just like it does in pandas. So this is actually counting the number of words, not the number of letters, just to be clear. It's the number of elements in that array, and then we're calling explode. Um, so we got rid of our array now, and now we've got one row for each word in that original category, but this num words column should still be there. Um, and then I'm doing a bit of filtering. So I want to get it down to just one word per category, right? So I'm going to get rid of a few words that bothered me. If we looked up here at our list of categories, or actually our bar chart of categories, you can see there's a word called ampersand. There's another one called 80. I just want to get rid of those because I know ahead of time, like if there's no letters in here, I know it's not going to be the kind of category I want it to be. The only exception to that was I did notice there was a couple of categories that failed this is alphanumeric test. Um, so I also say, okay, keep it if it's the only word. um, but otherwise, yeah, get rid of it if it's not alphanumeric. Um, and then uh, I have done this many times, and one of the words that bothered me that ended up being one of the final categories was item. So I'm just going to filter that out now, so we don't have to deal with it. Um, so yeah, we've got all of our words. We can see it's a bit bigger than the original because we do have multiple rows per um, uh, category, but we have those. Some of them have been filtered out. Um, I guess 80 wouldn't be filtered out because it is alphanumeric. So um, now that ampersand would be. Um, so that's our words. So remember, we're trying to get from category to just one word. So we have that mapping of, okay, what is the broader category associated with this? None of this has used our remote function yet, but now we will. Um, so here, again, trying to be as pandas compatible as we can, we're going to call dot apply on our series, our word series. Um, and we're going to apply this remote function. So we're actually going to run this lematize function that we just deployed to the cloud, and assign the result to this new lemma column. Um, so here, our lematizer looks like it didn't do anything for the rows that are visible. I'll show you one more feature. You might notice these icons up here. These are something you might have seen in Colab. It's a feature we call quick charts. But one such thing is just a different view on, in this case, we called two pandas. So on a pandas data frame. And so here we can, actually page through our data frame a little better. So we can see this Brandy's ended up turning into Brandy. So yes, our lemmatizer did work. Oh, and here's an interesting one, Barbados. I suspect our stemmer would have turned that into Barbado, but since it's a lemmatizer, it's a little smarter than that. Same for Schnapps. Um, it saw the trailing S, but knows that okay, that it's not necessarily a plural. Which is another reason to use a lemmatizer instead of a stemmer. Um, So yeah, we've run our remote function. We've got our lemmas. Now let's narrow it down to one per category. Um, so here we go. Um, I'll try to summarize this as best I can because I see we are getting closer to time. So I'm going to group by that lemma and sum up how many orders are associated with that lemma. So that lemma might appear in multiple different categories. So I'm going to add up the orders from all of the categories that it appears in. And I'm going to use that as my heuristic to say, okay, looking at these three words, let's say from 100 proof vodka, which one of those words appears in the most number of orders, and I'm going to pick that as my main word, and that's the heuristic I'm going to do for this mapping. So I'm going to count how many orders are associated with each lemma, um, and then I'm going to, in this case, I'm calling merge instead of join, and that's because I'm merging on a column, not the index. So um, that's something we inherit from the pandas way of doing things. Um, And then there's a trick here that I do um, down here. So basically, I aggregate by max. So I say, okay, now that I have the categories with the orders per lemma, let's find the maximum number of orders per lemma. And then I lose kind of the lemma information. So then I merge it back after finding the max, and then I say, okay, which lemma has that max? Um, and because there's some orders that might have exactly or some lemmas that might have exactly the same number of orders, I arbitrarily pick the first one in the alphabet. We'll see that American actually pops up quite a bit, so maybe I should have picked Min um, and gotten a little more accurate. But yeah, arbitrarily, I say, okay, well, if there's a tie, just pick the first one alphabetically. So I probably should have ran that because I think this query might take a bit of time because we've got several aggregations and several joins. Um, yeah, let's zoom to the next one just so I can get that queued up. Yeah, it's still running. But yeah, this should give us back to 103 rows, so one per category. Yeah, here we go. So we got one per category, and we've got a single lemma per category. So this is our mapping. Really, this column, category name, and lemma is what we wanted out of this. So we've got our way of summarizing or creating a broader category from these more narrow categories. So now I'm going to merge that back into my original data frame so that I can start doing aggregates by lemma instead of aggregates by category. Um, I did notice while I was doing this, there are some rows that don't have a category associated with this. Um, so this is another reason to kind of do your data exploration like this is you discover problems. Um, I haven't investigated which or how many don't have a category, so that's definitely something to um, maybe when we have more time to investigate and figure out why that might be. Um, and then I'm calling peak just to show. I'm gonna cruise through a little quicker just because I want to have some time for questions. Um, So here, yeah, so we've got, yeah, all our original data, our order numbers, and somewhere over here, yeah, is our lemma. So we happen to pick with .peak a bunch of mezcals, interestingly enough. So next, instead of zip code, I do want to kind of circle back to that geographic stuff. So instead of zip code, there's about like 1,000 different zip codes, I think, if I remember correctly, from when we looked at the dot describe. There's many fewer counties, about 100, just under 100 actually. Um, so let's aggregate by that and try to compare counties and see. I was curious, do different areas of Iowa have different tastes in terms of their alcohol consumption? So I'm going to group by both county and lemma and see, okay, how much of that particular, broader category was sold in that particular county. And since I'm going to be doing that trick before with the max, I'm going to create an integer version of that so I can use it for some joins in future. And in fact, in this next code sample. All right, so I found how much of each category was drunk. Uh, Here, I just want to figure out, okay, um, what is the most drunk thing in each county. So I calculate what is the max volume in each county, and then I say which I join back basically. So this is another way of doing joins. So yeah, which one sold the most? So here I didn't do the extra dot max trick. That's because the volume sold is so unlikely to be equal. Although maybe it was equal because I think we got a couple of extra counties here, so there might be some duplicate rows. And so yeah, we calculated each county. What is the most drunk thing? Um, so these are the most drunk things. Most of these counties, whiskey is the most drunk thing, but in Blackhawk County, vodka was the most drunk thing. Um, let's just compare, just get a broad picture for, how many counties have uh, um, are associated with each of these broader categories. Yeah, it's still taking a second. Yeah, I'll queue up the next one. So that's going to give us just like, okay, how many counties is whiskey their favorite? How many counties is vodka their favorite? And then there's a couple of oddballs that uh, possibly, well, these probably aren't whiskeys or something else. Yeah. And then here, I just want to get the uh, so this is the like per county differences. I want to get the statewide, and surprisingly, just like we had with the population difference, you might think just looking at the county data that whiskey's the favorite in Iowa, but actually, vodka is the most sold alcohol. So there's some counties that have a higher population that are pushing the vodka up, is my guess there. Yeah, we can see how much was sold of all these different categories, and yeah, we get a little peek at the different categories there. Um, so we saw a bunch of whiskey, whiskey, whiskey. There's one kind of fun thing I want to do here, which is to compare proportions instead of actual amounts. So I'm going to do a trick called the Cohen's H. And I do want to highlight one thing here. This line here, where we're calculating county proportions, that's using something that comes from pandas. So since we have this multi-index of county and lemma, and we have this index of county on these, um, you know, category per county as well as total drunk per county, I'm calculating the proportion per county just by dividing those two. And that's because we have these two indices with the same name. So it's actually doing an implicit join on these two index keys, which if you had to do that in SQL is quite verbose. But since we have this pandas API, yeah, that's like one of the fun things about pandas is you can do that division, and it does basically what I expected it to do, which is define the proportion. Um, and we scale that proportion up to get our Cohen's H principle. So we can see this El Paso County drinks a lot more liqueur than the other counties. Adams drinks more whiskey than would be expected statewide. And then we've got some smaller differences, but still larger than what would be expected down here. Side note, Adams County is not a county in, or El Paso County is not a county in Iowa. So again, we've discovered a potential data problem. I don't know where that El Paso is coming from. It would be curious to find which row that is. Next up, we've got one more public data set that I want to highlight, which is this counties geographic boundaries. So we have, I forget which government agency publishes these, but we pulled that into BigQuery. Very popular amongst our customers to use these boundary tables. So we're going to join up with that. If you remember from before, we've got 19 is how we represent Iowa. So we're just going to take our summary table here and pull in the geographic boundaries, download that table above as a GeoPandas data frame, so convert it into a GeoPandas data frame, and then use GeoPandas' plotting capabilities to show, okay, what is the thing about each county that makes it special in terms of drinking more than you would otherwise expect. So way at the bottom here, they drink way more schnapps than you would expect from the statewide averages. We've got some rum counties, some tequila, so we could discover some interesting things, or at least know what to drink if we find ourselves in the middle of Iowa sometime, what their specialty is. So yeah, we've only got a few minutes left. I do highly recommend. So if you've used your own project for this and it's not one of the trial ones, you can delete it. I've got a link with the instructions there, so you prevent billing. And I've got some recommended next steps. Just for fun, I'll show you. I did this exact same analysis, basically the same code on the USA names data set. So if you click through here and if we zoom in, we can see what the most Washington male name is. So it's kind of fun. Yeah, thanks everybody so much. One last thing, if you attended the talk, if you liked it, if you didn't like it, I'd love if you fill out the post survey. We've got a box there if you want the team to reach out to you. We're very active in developing this package and love to hear your feedback. Yeah, and that's all I had. We've got like 1 minute for questions. I'm not seeing any online, but yeah, thanks everybody.
Well, thank you, Tim, for that awesome workshop. I really enjoyed that. Up next, in half an hour on the AI ML track, we have From Features to Inference, Building a Core ML Platform from Scratch with Nathan Colbert. Thanks again, Tim.
All right. Yeah, thanks, folks.